So we prove the following theorem. If V1 to Vn is a basic for a vector space V, then any collection of m vectors in V where m is greater than n is linearly dependent. So here we have n vector in the basics, and we have m, a collection of m other vectors, or maybe this vector plus something, some other vector, so that we have m vectors. So any set of m vectors must be linearly dependent. It just means that okay, we only need n vectors. Now we have something bigger than n vectors, so they must depend on each other. So here's a way to prove it. We just consider, so let's suppose we have a set of n vectors. Say let vector u1 to um be a set of m vectors in V. We will show that they are linearly dependent. Okay, so we always start by considering a linear equation. So consider, say, C1 U1 plus Cm Um equal to vector 0 in V, when all the scalar C1 to Cm are scalar, right? In this case, let's say R. Okay, and then we want to show that U1 to Um are linearly dependent. That means we want to show that the scalar C1 to Cm are so the vector contains C1 to Cm. This vector is different from the zero vector. So in other words, it means that this system, or this linear equation, has a non-trivial solution, right? Something non-trivial. That is a solution of this equation. So now remember that U1 to Um are vector in the vector space V, and V has these n vectors as a basis, right? This means that any vector in V is inside the span of this V1 to Vn, right? Since V1 to Vn is a basis of V, and U1 to Um are vector in V. We have all of these Ui, I from 1 to m, can be written as a linear combination of n vector V1 to Vn. So U1 can be written as A11 V1, A12 V2, A1n Vn. U1 can be written as a linear combination of the vector in the basis of V. And this is true for U2, U3 until Um. So it's say AM1 V1, AM and Vn. remember that m is bigger, strictly bigger than n. Okay, so now come back to our equation here. This equation is equivalent to, now we replace on u1 by this linear combination, u2 by the second linear combination, um is the last linear combination. So this is c1 times the first linear combination plus c2 times plus until cm times is the last linear combination n equal to vector 0. So let's put them in terms. So v1, v2 and vn. So what is with v1? c1 a11, c2 a21, cm am1, v1 times v1 plus the last term for v sub n, so a1n. So this is for this coefficient of vn. So a11 times c1, right? So c1 a11 plus c2 a21, c1 a1n, c2 a2n, cm amn. This one equal to vector 0. Okay, now remember that v1, v2 to vn is, they form this set. v1 to vn is a basics of v, right? In particular, they must be linearly independent, right? Remember the definition of basics. This set v1 to vn must be linearly independent, and this set span the whole vector space v, right? So we use the first condition, they are linearly independent. Therefore, these equalities mean they are on 0. So these are scalar, right? They are scalar, on this scalar is 0. So, or in other words, this equality, this equation had trivial solution. So on this scalar are 0. This one equal to 0 and so on until this one equal to 0. Okay, so now what do we know? This should not here, this is because v1 to vn are linearly independent. Okay, so now this is a system equation, right? The a11, a1n, am1, amn on this one as amn, m1, they are on coefficient, they are on scalar in R. We know that. We know this scalar because they are scalar expressing vector ui in terms of v1 to vn. So we know that's a11, a12, a1n, am1 to amn. We know this. The variable here is c1 to cm, right? So this is a system or homogeneous system. Linear system with m variables and n equation, right? And note that m is strictly bigger than n. This system is underdetermined, right? We have m equation, we have m variables which greater than the number of equation. And this system is homogeneous. We know that it has at least trivial solution, right? So C1, C2, Cn, they are all zero, then it's good, this is a solution. But now is the number of variable is bigger than the number of equation. So we have free variable. Then this system has also non-trivial solution, right? The system has infinitely many solutions, right? Many solutions. Or what we just need is that this system has non-trivial solution. So has a non, in fact it says it many non-trivial solution. So C1 to Cm that is not vector zero, right? And what does that mean? That means that we start from this equality, this equation, and now we find that there exists C1, Cm such that there is at least one of them that is non-zero, right? This just means that this system has non-trivial solution. This means that the vector u1 to um by definition they are linearly dependent, right? And thus u1 um are linearly dependent, which finishes the proof.